graphic theory and diffraction theory. And I've given this brief disclaimer before, but I'm going to give it again. Those are by no means extensive, and you could cover entire lecture series on those alone. It's just to give us a brief whistle-stop tour to make sure we're talking the same language and things as we go on and have the same basis. So now what I want to come on to is thinking about the idea of powder diffraction theory and the theory behind it and how we're going to proceed. So if you've just joined the video now, very welcome, and hopefully things will be understandable from here on, even if you haven't watched that first set of videos as well. So we're going to talk about the idea and the theory behind what we're going to do in powder diffraction theory. So we're going to assume that we've got a sample that is crystalline, we've shone our X-rays through it or whatever instant wavelength or instant radiation that we're using through it, and we've got a powder diffraction pattern out the other side, and we now want to define what's going on. So the idea is very simple. The idea is that we can measure a diffraction pattern experimentally, and because we understand the physics of how the diffraction pattern should result from the structure, we can create a model, use that model to calculate a diffraction pattern, then compare the calculated and observed, and then gradually change the model so that we improve the fit to the data. And so ultimately we end up with a model that fits the data well, and so therefore we can be confident that our model sort of demonstrates the underlying structure of the material that we have. And mathematically, this can be done with a least squares fit. Now, it's worth just saying at this moment that this is a type of refinement. If you see what we're doing here is we start with a model and then change it to fit to the data. Therefore, we always need to have an idea of the structure or a model to begin with that we can change and define and fit to our data. It is not structural solution, it is a structural refinement whereby we are changing a model in order to match the data. So you need a model to begin with. Now mathematically, we're going to do this refinement with a least squares. So just very briefly to mention what a least squares fit is. Very often you'll have done this without even thinking about it when you're doing a fit to some sort of data. So if you've ever done a fit in something like Excel with a line, what you have is we put a line on it and we say that our line has a certain equation and we can calculate that, and we say y equals mx plus c is the equation of our line, and for each of our x data points we could calculate a theoretical y. And then we have an observed y for each of our data points. And what we're going to do is define a function r, which is going to be the sum of the square of the differences between the observed and the calculated. And what we're then going to do is we're going to try and change the values of m and c to change that line in order to minimize r, so create the best fit to the data that we possibly can. And so what we do in powder diffraction refinement is we're going to do exactly the same thing. We're going to calculate a function, which is our diffraction pattern, and then fit it to the data and try and minimize the difference between our observed data and our calculated diffraction pattern. And we can calculate that diffraction pattern from our understanding of the theory that we've gone through so far. We can use our knowledge of, if we've got a crystal structure, we can use things like the structure factor equation, and we can use things like the crystal symmetry and the space group in order to calculate where we expect peaks to be and the intensity of those peaks and things like that. And so we can calculate from our knowledge of the material and from a predicted model of our crystal structure what we expect that diffraction pattern to look like and compare it to the observed, and then try and use a least squares minimizer to minimize the difference between the observed data and the calculated fit. Now, to minimize the difference, so what we're going to do is our goal is to minimize the difference between the observed fit and the calculated data. So what we need to do is we need to understand how we can make one of them look like the other. Now, if you think about, if we go back to our example of a line fit, and we were to think about trying to make that line fit the data better, you would say, okay, maybe we need to shift the line up, or maybe we need to change the angle, the gradient of that line. And you would know, okay, if we needed to shift that line up, we would change, for example, the C parameter. Or if we were to change the gradient, we needed to change the gradient of that line, we want to change the M parameter. The same thing is going to be true here. We need to understand what parameters are going to affect what things about our diffraction pattern and our calculated fit. And so need to know what factors we need to change in order to improve the fit to the data. So actually, the way I think about this is in a very simple way. So this is the question that I want you to ask yourselves, is if you were to ask someone to describe the shape of a powder diffraction pattern to someone who has no understanding of diffraction theory at all so they could draw it, how would you do that? So take a step back from the diffraction theory for a minute and just try and describe what you see in a diffraction pattern to someone. And my very simple answer is that it would be described as a series of peaks sitting on some sort of background function. So mathematically, we could describe it as, this is my total function, some sort of background function with some sort of series of peaks sitting on top of it. So this describes the background function, and then this describes that family of peaks or that series of peaks that we have sitting on top of it. So then the question becomes, okay, we could describe the background function with some sort of function. What about the peaks? How do we define those peaks? And if we have a peak just like this, we might define the peak by various things. So we could define the peak by its position, where exactly we want that peak, by its shape, by thinking about its width, and by its intensity, by its area, how big or small that is. We could take that and scale it up without changing the shape. You'd just be making it bigger or smaller. So very often when we're describing a peak, we'll need to describe things such as intensity, position, and width. So for example, I've got the equation of a Gaussian here, and this has various mathematical factors that have things related to, for example, B here is related to the position, C is related to the width, and A is related to the intensity. So if we've got our diffraction pattern, and we want to try and improve the fit of the diffraction pattern to the calculated pattern to the data that we observe, what you need to ask yourselves at every point in the fit is, okay, what would I change in order to improve the fit to the data? So, and this is where this is totally general. At every stage, you should ask yourself, how does the calculated pattern compare with the observed data? And if I could change something about the calculated pattern so it better matches the data, what would I change? Would I change the background function? Would I try and move the peaks so they're better aligned? Would I make the peaks broader? Would I make the peaks bigger? What would you need to change about those peaks in order to make the fit better to the data? And then what you can do is start asking yourself, okay, what parameters do I therefore need to change in order to improve that fit to the data? Do I need to change the things related to the background, the peak positions, the peak intensities, or the peak widths? And each of these is going to have a load of different parameters associated with them, and each of them is going to have a physical meaning associated with that. So what would you need to change about each of those things in order to get a better fit to the data? And so what we need to think about now is each of these things, the background, the peak positions, the peak intensities, and the peak widths in the diffraction pattern, what do they physically relate to, and what parameters could I have to control all of those? And some of those, hopefully, from what we've talked about already or from your own knowledge of diffraction theory, you should start to have an idea about what might affect the peak positions or the peak intensities. Some of these things might be more or less obvious to you. But in fact, what I've done here is I've put together a complete table showing you some of the things that we may want to consider. Now, again, a brief disclaimer, this table is by no means complete, but see, these are some of the things that you might want to consider initially when doing a refinement related to peak position, peak intensity, and peak width. And so actually what we're going to do now is in each of the subsequent videos, we're going to take each of these in turn and think about them. What factors affect the peak position, what factors affect the peak intensity, and what factors affect the peak width. And we're going to cover those in more detail to give you a physical understanding of what they are and how they relate to something that we observe in the diffraction pattern.